If you don't tell me, how will I know?
It's just everything it gets like whited out. It's weird.
Sorry about that. Okay, perfect. So let's see what we do with this. I told you that 2 to the x and log base 2 of x are inverses of each other. But I don't want you to trust me. I want to show you why. So let's take a look at two bubbles. Give me an exponential function. Any exponential function that you want to work with for a couple of minutes. Any exponential function. We can use the one we looked at last time, or we can just look at another one. Let's say 3 to the x. Let's choose three x values. I'm going to use a -1, I'm going to use 0, and I'm going to use a positive. And now I'm going to ask you, what are the y values? So if x is -2, f of -2 will be 3 to -2, which we know is 1 over 3 squared, which is 1 over 9. When I plug in 0, 3 raised to 0 is 1. When I plug in 3, 3 raised to the third power is 27. And now I told you that the inverse function is f inverse is log base 2 of base 3. Bases have to be the same. Base 3 of x. Okay, so and now I need to show you that when we apply log base 3 to 1 over 9, what should the answer be?
-2.
Right. When I apply log base 3 to 1, what should the answer be?
0.
Right, right. And when I apply to 27, because otherwise this is not the inverse function. If it does not take this back where it came from, if it does not take this back where it came from, and all the other numbers back where they came from, then it's not the inverse function. Now I'm going to use that.
We can't see what you're pointing to. There you go.
I'm going to use this to show you. Okay, perfect. So let's apply log base 3 to 1 over 9. I'm going to say I have no idea what this is. So that's my left-hand side, left equation of the double equivalency. Log base 3 of 1 over 9 equals y. And I have no idea what this is, but I know how to convert it. 3 raised to y equals 1 over 9. 3 raised to y equals 1 over 9. So now can we figure out what y equals to? Let's say we don't. So then the left-hand side is 3 to y. The right-hand side I know is 3 to -2. 1 over 9 is 3 to -2. The bases are the same. The two numbers are equal. So what could y be?
1.
3 raised to 1 will not equal 3 raised to -2. Is that clear?
Yeah.
So what could y be then?
Zero? No.
So if I put 0 here, 3 to 0 cannot equal 3 to -2. So these two numbers are equal and they have the same base. The exponents must be the same, otherwise the left-hand side will never equal the right-hand side. So now we showed that when we apply log base 3 to 1 over 9, we recover -2.
Oh, okay.
Better?
Yeah.
Perfect. So now we apply log base 3 to 1. I don't know what that is, but I know that I can change this into an exponential equation. Can anyone give us the exponential equation now?
3
3 to the y equals 1.
What could y be? What can I raise 3 to get 1?
1.
3 to the... Yes.
No.
You understand that 3 to the first power cannot equal 1, so it must
Right.
be 0. Is that okay?
Yeah, okay.
So then we apply log base 3 to 1 and we recovered 0. Final step. I know I convinced you already, but let's look at the last number as well. So log base 3 of 27 is, I have no idea, but I know how to change this log equation into an exponential equation, and that would be 3 raised to y equals 27. So which number I raised 3 to get 27?
3.
That number is 3. So there, thank you. So therefore, when we apply log base 3 to 27, indeed we recover 3. So therefore, we conclude that 3 to the x and log base 3 has to be the same base of x are inverses of each other. Now here's a question. If I say log base 2/5 of x and ask you what is the inverse function of this, what will you say? What could be the inverse function? What type of function has to be? It has to be. What type of function is this?
Exponential.
Very good. What type of function is this?
Log.
Very good. What type of function is this?
Log.
Perfect. What type of function will the inverse of that log be?
Exponential.
Very good. What is the base?
Right.
The base must be exactly the same base. Yes, exactly. See, this base is 3, this base is 3. This base is 2/5, this base has to be 2/5. That's how it works. Questions? Two special log functions before we continue to look at something else. We had, remember in the exponential, we had two special exponential functions, 10 to the x and e to the x. Of course, in log, we're going to have the corresponding ones. How come? Here's why. Right here, we see e to the x, that is activated with the blue key, e to the x, and we have 10 to the x that is also activated with the blue key. The same key is shared with some logs. This 10 to the x, which is the common exponential, goes with a common log. This, which is natural exponential, goes with a natural log. So these are inverse functions. So then, the corresponding for 10 to the x, it will be just log x. There is a phantom 10 here. We don't write it. By convention, we don't write the 10. Same thing here. This one will have that ln x. Well, what is this? Well, it's the same. It has base e, but we don't write it. It should be natural log, NL, but it comes from German. That is log natural. So here are the two keys. Again, log, this one, and ln, this one. Now, let's go back to the graphs of the log functions and identify something very important. We said that the exponential function is friendly. It's defined for any x. For this x, for this x, for this x, for any x you want. Same thing here. For this, for any x. All real numbers. But that's not the same case with the log function. As you see, the log function, the pure log function, is defined on 0 to infinity. The pure log function, the green function here, is defined on 0 to infinity. So this is not a friendly function. So we may be given something like 76 on page 490, in which we are asked to find the domain of this function, log base 5 of x plus 6. If you ask me to tell you the domain of log base 5 of x, I would say no problem. X has to be greater than 0, so the domain is 0 to infinity. But here we don't have log of x. Here log is applied to x plus 6. The same way, I would have to write that x plus 6 is greater than 0, which will mean x greater than negative 6. And we know that this is a transformation. Anyway, we knew that. So when we change x into x plus 6, the graph shifts 6 units to the left. If the pure log function is defined on 0 to infinity, and this one is a shift 6 units to the left, obviously the domain now is negative infinity to 6. This is an important concept. So let's look at another example. Same page, 78. And 78, we have f of x equals log 7 minus x. First, I want to ask you, what is the base? There is no log without a base. What is the base here? I don't see a base. What can it be? When I see log, I know it's base 10. And the same concept, everything the same. I have to write that 7 minus, I'm asked to find the domain. That's the same question. 7 minus x must be positive, or negative x must be greater than negative 7. And I multiply or divide both sides by negative 1. And what happens when I multiply or divide both sides by negative 1?
The sign switches.
Very good. So in this case, the domain of this function is negative infinity to 7. I would like us to look at applications. There are many, many applications of log function. Let's take a look at problem 119. 119 on 491. I'm going to copy that for you in a moment. Let's see what they want. Students in a psychology class took a final exam as part of an experiment to see how much of the course content they remembered over time. They took equivalent forms of the exam in monthly intervals thereafter. The average score, f of t. So I'm going to copy that. I'll come back to it. So first, this is problem 119 on page 491, and we have a function f of t, 88 minus 15 natural log t plus 1 for t between 0 months and 12 months. So this is in months, and f of t is the average score. Average score. So the average score for the group f of t after t months was modeled by this function. What was the average score on the original exam? What was the average score after 2 months, 4 months, 6 months, 8 months, 10 months, 1 year? And sketch the graph. Okay. So part A and B, whenever we are asked for original or initial or beginning, what are we asked to find? What was your age when you were born?
Yeah.
Exactly. So every time we talk about original, initial, beginning, we are asked to find f of 0. Then they want up to 2 months, up to 4 months, 6 months. Is 8 in there too?
No.
Yeah, yeah. 8, 10, and 12. So, of course, I'm not going to do this 10 million times. I'm going to do this 0, 2, 4, 6, 8, 10, and 12. I am going to put the function in the graphing calculator in y equals clear if you have anything else in there. And punch in 88 minus natural log right here, this key, natural log. It's x plus 1, and close the parenthesis. Do we all have this?
Yeah.
Now with the second table, and I'm going to punch in all these numbers one after the other. 0, 2, 4, 6, 8, 10, and 12. I got all the numbers. Unless I made an error, because they appear to be all the same. Yes, because I forgot the 15 in front. I'm so sorry. Okay, that's a different story. Okay, at 0, 88%. I'm rounding up. 71.5, 72%. 4 months, yes, 64. After 6 months, 59. After 8 months, 55. After 10 months, 52. After a year, 49, roughly 50. Now I'm asked to graph this. I have so many ordered pairs, more than enough for me to graph this. So let's see. 2, 4, 6, 8, 10, 12. Okay, so the smallest is 50, so I'm going to say this is 50. I'm going to break the graph and say this is 50, 60, 70, 80, 90. And I'm going to plot the points. At 0 is 88. At 2 is 72. At 4 is 64. At 6 is 59. At 8 is 55. At 10 is 52. And here roughly 50. So this is the graph of 88 minus 15 natural log t plus 1. Like any other function, but it just has a special graph. Okay, let's look at another word problem.